So the next lecture is by Dr. Tomasz Soltinsky. He's going to talk about 21 centimeter forests. And it seems like we're changing subjects completely, talking about botany. No, you know that that's not what this is about. It'll be about 1 hour again, and the lunch will be at around.
Okay. Thank you for introducing me, so I don't have to do that now. And just the thing that I want to point out, please interrupt me at any point if you have any questions or comments now or during the next couple of days or later on this email. I'll be more than happy to discuss anything about 21 centimeter signal with you. So then, yeah, I'll be talking about 21 centimeter forest. Okay, that's okay, so the things that we'll discuss is, okay, first of all, I will describe what the 21 centimeter forest is, how it differs from the other 21 centimeter line observables. Then how we can model this signal, because of course that's what we want to do. Then I will try to describe some motivation behind. Oh, okay, sorry. Makes sense. Okay, yeah. Okay, so yeah, then I will describe some motivation behind why we should actually care about this signal, what we can learn from it. And I will go briefly through the prospects of detecting the 21 centimeter forest now and future. And today, what I want to talk about are the first 2 points, and tomorrow the rest. Okay, so first of all, people before me discussed, for example, the global 21 centimeter signal and or tomography, for example. And what you usually do, well, you have to have some radio background to observe the 21 centimeter line comparatively to that. And usually what you do, you use cosmic macro background, right? But the problem is that between us, so for example, the telescope in Pune, UGMRT, and the CMB, you have some strong foreground. So this has been discussed, I think, by Sarah. To some extent, at least, and so yeah, this could be some extragalactic sources or even our own galaxy. So this is the radio map of the galactic center from Meerkat. So yeah, and because of this, because these foregrounds are very strong, this causes some problems. So here are some observations of the 21 centimeter line, cosmological. 21 centimeter line. So on left, you have reported detection of the global 21 centimeter signal or sky average 21 centimeter spectrum. So that's that solid line there, curve. So this is reported by edges, and so these frequencies correspond to redshift around 17. And yeah, so they reported this detection in 2018. However, Indian experiment SAS3 reported no detection at in this frequency range indicated by this gray shaded region. So obviously this is in disagreement. So this is, I guess, controversial. So we're still not really sure if this is actual detection by edges or no. And this is, I guess, one of the main reasons why this is such a problem is, again, strong foreground, because it is very hard to actually do the detection. Then on the right, you have power spectrum constraints, upper limits on the power spectrum calculated from or measured from the tomographic measurements by different observatories like MWA, Paper, LOPAR, GMR. These actually can extend to higher redshifts and lower redshifts as well. I just showed the epoch of reionization bit, and you see that this pink point there, that triangle from Hera, the tightest constraint that we have so far, this as far as I know, you see that this is still 2 orders of magnitude higher than the theoretical predictions in these black curves here. So, and again, this is, I guess, mainly because of the strong foreground. So there's been a lot of effort put into filtering them out, modeling them, trying to dig out the signal from the observations. There are some papers there. But yeah, however, we, to some extent, I guess we are lucky that there is an alternative. So I'm gonna ask you now, so what do you think, what else, what other radio background can you use besides the CMB? So does any of you have any phrases? Okay, yeah. So that would be one option, is maybe something else. Go. Okay, well, yeah, first of all, radio loud quasars. So that would be one good option. Another thing that people consider is gamma ray bursts. So both of these are just artist impression, how these things look. They kind of look similar, but don't be confused. The quasars, that's on the scales of parsecs, and gamma ray bursts, that's floating star. I think that's the those are the so they're very different but yeah, they have been considered to be a good radio background sources for 21 centimeter forest. So that's the main difference. Instead of using CMB as your background source, you will target your telescope at some radio loud point source, quasars. Okay, so maybe I should go briefly through what quasars are. So they are a type of AGN, or active galactic nuclei. So basically very bright centers of galaxies. So yes, they are very bright. For example, they can be even thousands of times brighter than our own galaxy, and that's, we are still talking only about the central part of the galaxy. But they are very compact. Like I said, they're small. They're in the center. So again, compared to Milky Way is 20 kiloparsecs large-ish, and the AGN are just a few parsecs. So kind of 2 different extremes. And what we think is happening is that they are powered by infalling material into them. So you have basically a black hole, supermassive black hole. So yeah, a million or billion solar masses object. You have some accretion disk around it, and so some material, and this material impulse in, it heats up, and then it radiates, and so it changes. This material changes its gravitational potential energy into radiation through, like, it changes it in a very efficient way. So again, just to compare the numbers, so this efficiency can be around 10%, and nuclear fusion, which basically powers the stars, is only, it's not even a percent efficiency. So you see that this is a very, very efficient thing that is happening in the universe. And yeah, so the name just comes from the quasi-stellar objects. So they basically, on sky, they look very similar to stars, but they have very different spectrum from black body, which stars do. So just to prove this point, another question for you. So these 2 things that are in the middle, one of them is quasar, one of them is star. So which one is which? What do you think? Okay, let's do this the whole class. So left one, is that a quasar? What do you think? Okay, okay, fine. Okay, the right one, is that a quasar? Okay, few people. Fair. It was, I guess, more or less the same number of hands up, which is good because that just proves my point that you can't distinguish them. But I'm going to give you a hint now. So the left one will have spectrum slope scale. So the left one will have something like this, and the right one in axis will be like this. Okay, so once again, left one is that a quasar? Right, yeah. So because this is it should resemble black body spectrum. Sorry for my drawing skills, but yeah. So yeah, that one is a quasar. So you really need to look at the structure of this object to find out like which one is which. Okay, so let's talk about the structure of quasars or AGNs and where does the different parts of the spectrum come from. So again, in the middle you have this supermassive black hole, and you have this thing. I'm not sure if you can see that accretion disk of material from this. So this one radiates like a black body actually, just it's up and that stuff. So that would be that blue part of the spectrum in optical for UV. Then also in the accretion disk, you have a layer of I think hot plasma, we call it hot corona, that radiates high energy photons. This corresponds to this X-ray part in light blue or side. Then besides that, around the accretion disk, you have this huge dusty obscuring torus. I will not go through details why do we think it is there, but this will absorb photons and we emit them in the infrared, the red part there. And what we care about are these relativistic jets. So the AGN is shooting these jets of material perpendicularly to the accretion disk. And because of the synchrotron radiation, which was talked about by Sarah, they will radiate in radius. That's what we care about because of much physics. Okay, so yeah, like I said, this comes from synchrotron radiation. So basically, you have these particles, ions, and they, because of the magnetic field, they spiral and they will radiate synchronization with radio. So the usually what we do is that we model the radio spectrum of this quasar as just a single power law. Fits quite well, as you can see. These are actual observations of this distant quasar, which is a bit special, but I'll talk about it in a second. So how do we define what is radio light? Yeah.
You also expect the system.
Yes, I'll sorry. So that will be actually, this turnover there. So that's modeled here. So people do expect this. Actually, this is from this paper about the Muslim. They actually want to find this turnaround point in various places. So check out this paper if you are interested in this. It's really nice. They also have some measurements for this power law. It's also nice. Okay. Okay. Yeah. So how do we define if a quasar is radio loud? So it's another simplistic way. I'm not really sure how easy it is to actually measure this, but it's basically this ratio R. So you have specific intensity in radio at 5 gigahertz. You divide this by a specific intensity optical at 4400 angstrom. And if it's more than 10, you say, okay, this guy is radio loud. It's a bit yes, arbitrary, but people have been doing so. Yeah, just for classification purposes. Okay, and the reason why this thing is this particular quasar is interesting is because it's laser. So lasers are this special kind of AGNs that basically so they are just a normal AGN, but this relativistic jet will be pointed to. So it's just a matter of the orientation of the quasar, and then these things we call lasers, and we expect them to be loud because just points that relativistic jet to you. Okay. And okay, so let's discuss what the 21 centimeter forest actually is. So it's you can see an example here. So this is just simulated spectrum. So it's a series of absorption features imprinted in the spectrum of some radio loud background source like gamma ray bursts or radio loud quasar, and this arises from the intervening neutral hydrogen structures. So basically, if you have some filament in the cosmic web, which is neutral, full of hydrogen, then that will leave an absorption feature in the spectrum of your radio loud background source, and of course, this arises from this hyperfine transition. Of course, heard about this many times because that's why we are here. Okay, so to explain maybe a bit more how this happens is that okay, so you will have at the beginning you have radio loud quasar, let's say, which will emit the whole spectrum of photons. This okay, so let me just explain what is going on here. So the top you will have density field along the line of sight from us to this quasar. Then the second panel is the neutral fraction of the hydrogen. Then you have spin temperature, and then that's gonna be the radio spectrum of that quasar. Okay, so initially it radiates this whole spectrum of photons. So you see it's a power law, not very steep because the thing is just stretched. Then these photons travel through the universe. They get redshifted, of course, because of the expansion of the universe, and some of them will be redshifted to the 21 centimeters wavelength, as you can see here. Okay, and then what happens is that some of these photons that get redshifted to 21 centimeters, 21.1 centimeters, they will encounter this neutral hydrogen structure. So you can see this peak in the neutral fraction. So that's yeah, so that's almost completely neutral, and then you can see that this structure is also very cold. So, and when they hit this structure, some of them will be absorbed, and this will leave an absorption feature in the spectrum of this quasar, as you can see here now. And then the rest of the photons travel further, they get redshifted, they hit another structures, and get redshifted, and so on and so on. And this leaves this, series of absorption features, which I guess some people think that they look like a forest, hence the name of this signal, 21 centimeter forest. Yeah. Are there any questions so far about this main idea of the signal? Okay.
What is the
Yeah.
we have that
Okay. Well, so actually, what you can do, you can basically use normalized flux. So your spectrum will be basically just one initially at all places, and then you just calculate how many photons in terms of fraction the photons will be absorbed. So basically, you can imagine that this will be not a power law. This will all be just one. You can do that. But otherwise, if you want to do like actual observations and these things, which would be very useful, yes, you definitely have to model that. Not only that, of course, the instrumental features and these kind of things, but like I said, we usually model it as a power law. It is harder for some other, I guess, signals because you might have interesting features around alpha for so that might be a bit more complicated to actually model the intrinsic spectrum. But yeah, definitely.
There are too many absorptions. Finally,
Yeah. Well, I don't think it really matters much because it's like you can see here, it's it's also some absorption. These might be similar things might be bigger problem for Lehman alpha 4s again because just that might be saturated. But that's different story. Let's not really talk about this. Okay, let's move on. So, like I said, there's only some 21 centimeter photons are absorbed. So let's go through why I say only some, or how can we measure that, like how many. So I will talk a bit about the radiative transfer equation. So I guess you've seen this before. Basically, what happens here is that the change in the specific intensity of the light that comes to you will depend on. So this is you, observer, and you have some quasar, and the light goes you, but you have some hydrogen, hydrogen cloud. What can happen? That some light photons will be absorbed. So this is given by that first term, and this kappa is just the absorption coefficient. I think you reached that yesterday, but called it alpha. Using you, I apologize for this, but the same thing. And uh, and then photons might get given by J. Yes, this path lines basically how much you travel through this hydrogen gas cloud. Okay, and so we have this equation. Now we can define some of the things. So optical depth will be given by that thing there. And I think let's discuss this yesterday. So yeah, if we plug this in, uh, change and we also plug that into second term, which will get the okay. Then we also define source functions, so the ratio of these two things. So yeah, the whole equation. Uh, uh, now this guy, and let's take all of the densities terms on the left side. Uh, okay. Okay. And now, what we can do, I okay, I'm not missing any steps there. Now you do this. I don't know. I always found it this random mathematical steps. You just multiply it by the integration factor. E new right side. Oh, okay. Now we have this. This we can use chain rule to change this thing to this. Okay. So and now it's in the form that as we can write. So we integrate this. We'll just write it, and it will be integrated from basically this point. So here the optical depth will be 0, and at the endpoint, let's call it new. So we'll go from our prime equals 0 to this. So left hand side, I'm changing the that we are integrating over. So this thing will change to prime. And well, so thing. Okay. So yeah. So if we just play this, we will start with this up minus 1, of course, and we'll have some density at so our radiated, and let's not do this part here. We'll copy this. Okay, and okay, so know that this equals 1, but let's get this guy here. So again, we'll apply the whole equation by e to the minus tau u. So this will become out, so you are left with this thing and minus u. Yeah, multiplying 0 and plus this. we put the factor that we are integrating here in these expressions from this thing, this. Okay, and basically the last step would be bringing this thing to the right side so that our left side just our final state of the bottom budget that we are left with, and yeah, so that is just the integral form of the equation of the radiative transfer. So you've seen this before in slightly different form. I think both Preston and Girish had this, but this was not in terms of this I, but in terms of the brightness. But as you seen yesterday, some factors. Okay, so now we have this. Yeah, and well, actually, okay. So yeah, and so basically, what you see here. What you see here is that so yes, we basically how to say so the as the photons travel through this neutral hydrogen cloud or some elements on some structure, initially they have this I zero, but at the end what will happen is that you basically have just that term, so the initial amount of photons times e to the minus optical depth. In the 21 centimeter forest, we don't really care about that source function from there. So basically, your spectrum, your flux, is given just by this very simple depth. But what is the optical depth? Of course, we need that, and that's given by this formula here. This is approximate formula, so it's simplified. I will not go through the derivation of this, but yesterday it was discussed. So I think Girish, if I'm not mistaken. But yeah, so so it's just a bunch of constants in front, and it depends on the how much neutral hydrogen gas you have, and the spin temperature, and universe. Okay, so but to get maybe some sense of what numbers we expect, what we can do is firstly we'll assume a matter-dominated universe. So H becomes this. We will plug in some other expressions. So for the neutral hydrogen number density, so it's just a bunch of these things. NHC will be that's just mean number density of hydrogen. Rho C is chemical density of the universe, which comes Friedman equation, so on. And basically, if you plug in all of the numbers and these things, you end up with. So I have prepared you the homework, and basically the first part of it is just go through this derivation. Should be fine, but if not, just ask me. I'll help you with that. Okay, so now that we have this, um, so depends. It can be very low, then you will have no signal. It can be one, which is 100% hydrogen. What obviously what you want here is as high as possible, as strong. Basically, this tau you want it as high so that the absorption. But it depends what are working. But if you some signal, really depends. It depends. If you, for example, base the whole thing on simulations, where the epoch of reionization, so we are talking about epoch of reionization this whole time. So we'll have ionization bubbles where XH1 is 10 to the minus 5 or something very small. Or it will be basically. And depending on that, where at the, if you remember that animation, in that some bits were neutral, states were ionization bubbles. So, basically.
NH1 would
Or both, which is usually have just over 10. By normal. It could be homogeneous, like okay, everything show everything density. The like what that's actually ours. The same thing goes for the temperature. You can calculate that from temperature of the gas, and or you just assume the capital is strong at these redshifts with all the stars there, galaxies, and say okay, temperature. If you're any so I will actually discuss this tomorrow, but basically from up to the highest radio loud quasar that we detected is at 0.82.
Yes, by redshift, it's something, isn't it? It is already pretty much ionized.
No. No. I will discuss this again tomorrow, but the bottom line is that now we think reionization and other chip 5.3. So we will still have some neutral hydrogen. Then hopefully we'll detect some really low quasar hydrogen because actual quasars there are some at hydrogen. I think there are some, but we'll see. We'll see. So that's just one second. Actually, in the homework, I compared this to the Lehman alpha forest. So go through that going on. But of course, there is different physics between things. But this by nature, you mean in nature by the depth or the shape? That depends on quite a few things. Actually, in a few slides, I will talk about this. But reading it. There are other processes. We have either you know thank you for because you have query for almost hydrogen or there are some stations. Like I said, okay, let me move further. So, yeah, so I said this before, but you can divide everything here in terms of flux and in particularly normalized flux. So basically, so your F0 will be 1. So this thing will be 1, so you're left only left you will have transmitted flux. Transmitted. This F21 will be turned into percent rather than physical values. Okay, but let's get some intuition on what kind of numbers we expect. So here, okay. So let's have let's assume just to make it simpler, range 9. So that's right most term will be 1. Let's assume neutral, completely neutral hydrogen, so XH1 is 1. So the only things that will change now is the overdensity and this. So temperature Kelvin and 1. The couple of numbers. Let's assume in density, so 1 and for 10 Kelvin, so something very cold. So tau 21, this case will be 7. So almost 3% absorption, not much, but it's doable. We might be able to observe that, but this is just to give you an idea of even in this very cold case, the signal is only 2% absorption. Maybe what we can do more feeling if we increase temperature to 100 Kelvin, change to is even less than. So even in the case of name it let's call it warm intergalactic medium, not even hot 100 Kelvin as well. The signal will be already very close. So if you go below 1%, anything. And but if you go back to say this kind of thing, so where can you find? So now there are these objects called mini halos. These are just dark matter clumps with sizes or masses of less than 10 to the 6 solar masses. So they're big in terms of every day life, but in large scale structure they are not that huge, and I'm not sure if you can see that very well. But so on right, I show some results from simulation, and you see the cosmic web structure there. And there are these bright spots here and there, these pink or white ones. That's your. However, problem with these mini halos is that if you give it only maybe a bit of some energy input, feedback from star formation or they will photo evaporate. Basically, see that even after 30, 40 mega years, you lose a lot of structure. So given this, we're not really sure how much mini halos contribute to actual signal universe, because, like I said, you just give it a bit of energy input and you will use these structures. Another issue with these things is they're very hard to simulate because of the cosmological form, because of simulation resolution. So here on left, so on right, on the side you see there's only 200 kiloparsecs over age. On left, you see that the simulation box 80 megaparsecs, much larger, with larger scale structures. If you zoom in, you see that these blue circles, they correspond to the halos. They're smaller than the simulation resolution. So it is really hard to simulate them, and many simulations don't capture them at all. So yeah, so these are the challenges these guys. But okay, let's say that we want to look at some larger halos, or some with a larger over density. So let's go to it. Density. Tell me, and you get out of this 27% absorption. That's a lot. Be nice. But I have a question for you. Do you think that these numbers, this high over density and this relatively low temperature, is that realistic? Get that in the fucking. So in our simulations, at least, you can't get that. So here I show the phase diagram of the temperature on the vertical axis and density on the horizontal axis, and you can see that if you go to 100, so that's 2, of the over density, you only have hot gas. This is because the overdense gas, you expect there to be shock heating, a lot of star formation. These stars will heat up the gas, and basically how it will look. And the color map, I show the tau 21 for a pixel with these properties, with this temperature and overdensity. And you can see in this yellow, that's where the strongest absorption happens. So you see that this happens in the fuse called intergalactic medium. So that's where your strongest absorbers come from. So they are slightly overdense, between 3 and 10 in delta, the overdensity, and they should be below 100 Kelvin. Otherwise, the absorption is suppressed quite a lot. Okay. So, but this line as promised. So if the course, your line is not just a literally line. It will have some shape, will have some width, some depth, and this is given by the motion of the particles involved that absorb the photons. And if they have Gaussian velocity distribution, and if the tau is less than one, around one and less, you can approximate this line profile for 21 centimeters as a Gaussian. So that's given by that right there. It's basically looks like this. Yeah. And so this shape, or the width of it, can be given by different line broadening mechanisms. So there is thermal line broadening, and this is given by that factors. That's a Doppler parameter. And the expression for that is very easy, a couple of constants. So that's the Boltzmann constant, and divided by mass of the hydrogen atom. And what changes is the okay, so given you have the line profile and the expression, or what it depends on, and your Doppler parameter. Question for you, another one. So if we increase this TK, so this gas temperature, what will happen to the line? Will it get wider? Will it get thinner? Will it be deeper? Will it be narrower? You can work in pairs. I'll give you time to think about this. Yeah, yeah.
Question, do you mean if the minus 2 square?
It's just yeah, minus of plus.
That's frequency.
Okay, I mean, I was thinking about velocity of the gas, more or less, but it's basically. Well, okay, no, it would be incorrect actually to think as a frequency, because B is given in velocity. I will talk about this. Okay. Okay. Fair enough. Yes, you're right. Yes, the correct answer is C. So this thing will change if you increase the temperature. Okay. Another effect that can line broadening is the velocity of the whole gas cloud. Redshift space distortion. So now that the universe expands, everything goes away from us. Is this bubble flow of the structures? But then besides that, you have peculiar velocities. So this is just because so you have this bubble flow, everything goes away from us, but some gas can relatively to this bubble flow, it can move around. So if you have some very massive overden structure, the gas might go towards that. Besides that, you might have some hydrodynamics, like shocks or whatever that can push the gas. So it's not only that everything goes away from us, but there is some hydrodynamics gravity that plays a role there. So there is additional part that velocity quantity there. And so to include this effect, you change, if you remember, you change your H for the optical depth formula to these guys. So that's 1 plus E and TV parallel over R parallel. This is just the the velocity gradient along the line of sight, and write this basically couple flow plus we have both of these terms. This is still just the approximation, and there might be some problems. In some extreme cases, what might happen is that this guy, this gradient will be negative, like it goes. No, I don't think so.
So this is just a question.
Of course, it just includes more physics. You assume register, you assume peculiar velocities as well in this. You assume both. You assume Hubble flow, which you had before in the Hubble parameter, but you also
We adding this term to
adding it in some sense. What is the peculiar velocity? Yeah, yeah.
we are in both Hubble perspective.
Yeah.
Okay.
Yes, thank you. So you have this, yes, there, like plus,
Oh,
but now getting numbers from this, you need some more, which what can happen? What happens to me actually, besides that, is that if this is negative, so the gas comes towards us, something happening, gravity or something, and if this is larger than this all height will bend, all external will be active. Will have negative optical depth, which doesn't right, and your normalized flux will be more than 1, minus minus. So, so yeah, just be worried that not like, so you might get some physical results, but my point, what I want to make is that it's fine as long as you work within the assumptions you make for your approximation, I guess, for any mass that you calculate. So, like I said, it's fine to use, but you need still like somewhere in the back of your mind that okay, I can use it now, but maybe the case that I describe here is a bit extreme. But this happened to me, didn't make sense, but then I realized, oh, I see. So yeah, the personal experience. Okay, so uh, just have a feeling that some people just decide not to. Any studies, they just maybe or they just have to. Yeah, that's another thing. Like that's you assume they will not affect your results. You should first make sure if they do or not. And yeah, yeah. Okay. Tomorrow I will actually discuss this. What the impact of the peculiar velocity. I don't know how this works. There are differences. So yeah. In my opinion, if you include more physics, more realistic. But of course, you might be limited computational or math, hard to solve practical. So yeah, so I've been saying that we have these approximate relations or formulas. So what we can do instead is can use more numerical approach. We will use simulations, logical simulations. With these simulations, you can model a lot of physics, like a lot. For example, evolution of the reionization. You see in this animation, this is from our simulations that we use. You see that these ionization bubbles, they form at different times at different places. They expand, they overlap until they fill in the whole volumetric ionization. Hence, model that. Besides that, you can model the hydrodynamic response of the gas to reionization. Okay, let's play this. First of all, okay, you see this white line there. So that's the ionization front. Then you see that the gas responds to it hydrodynamically. So it's heats up and some structure is low. So let's play it just again. So on top, it's just the now you see that changes. So I will not go through the details what's going on here. Really, the point I want to make is that you can model the hydrodynamic of the bonds gas to ionization basically, and we do that in our simulation. So Sherwood Relics simulation suite. Feel free to check it out. If you just Google Sherwood Relics simulations, you should find it. Don't Google Sherwood Forest or Sherwood Nottingham because you might get some pictures of actual forests and Robin Hood or something. But yeah, please check it out. Or there is a nice overview paper by our collaborator about the 23. So learn about that there. Okay, so simulations, the output that you get is density, Becker velocities of the gas, neutral fraction, temperature, and these things. What we do for 21 centimeter forest, forest, but that you have your simulated box and you draw some random skewers, so line of sight data from through this simulated box. And this is an example of what you get. So on top you have over density. I'm very sorry for a very small font, especially people on the back, but top is over density. Then you have Becker velocity, neutral fraction of the gas, of the hydrogen, and the temperature. So black is kinetic temperature, the orange is spin. And once that you have this, you can calculate the optical depth and F21, which we do in the bottom. So now you see that this form of this equation is a bit more complicated, longer. On left, you are still you have more or less the same constants. And what we do here on right is we convolve over the whole line profile. And this is just how it looks. So this should be actually integral, but given that your data is within different cells, different pixels, you can do a sum over these pixels. And how to think about this is that if you want to have optical depth tau 21 for the pixel I, what do? You take the Hubble velocity of that pixel, and then you have to go through all of the pixels, their properties, their temperatures, their densities, Doppler parameters, and you calculate this expression, the sum for each of them. You sum. And here, the uj is just the sum of Hubble flow and Becker velocity of a pixel j. So we include both of these effects in here, and we can see that whatever are these numbers, whatever, negative, positive, that thing in the brackets will be positive because it's squared. The whole thing in the exponential will be negative. You don't get physical results there, at least not because of the Becker velocity. So that's one thing less to work. writing this down. Maybe I can ask if anyone has any questions on this.
Days, Lisbon,
J just goes through all of the pixels. So you have you want to calculate this thing, you have to go through all of the. There are some tricks there. So I think periodicity of the and your box, which cosmological say that they are periodic. You have a box, the box next to each same, but just boundary. But fix there. Okay. Let's. Okay. So given all of these things that I discussed, I have a last exercise for you for today. And can you think of any advantages of 21 centimeter forest versus other 21 centimeter line of observables? Again, work in pairs. Ask between.
they give the amount of representation along the line.
It can, but
The big thing,
or you actually you can probe the structure, not only the amount of I guess hydrogen, but also that would be, that might be hard with this guy average. That's yes to that the structures. Okay, so that's what do you mean again? Yes. That's actually okay. So the Gambit-Peterson drop would be basically you have no Lyman alpha photons that are transmitted. So there is just nothing. So you can't see anything. So that is a very important point actually for your homework. Yes, 21 centimeters. So that's why Lyman alpha forest is you see that in ionized and hot. Some photons are, and that means that at the end of the epoch of reionization, when everything is hot and ionized, you can see Lyman alpha forest. You can see 21 centimeter forest because it's hot and ionized. But if you go beyond redshift 6, let's say, when universe is at least partially neutral, that's when we have problem for Lyman alpha forest. Yeah, Peterson drop. Everything is absorbed. Don't see anything. Which is also useful information, but yeah, but 21 centimeter forest, in principle, you should. So yes. And then yeah, I'll give you a hint. Beginning of my talk, I was talking about different background sources. So does that give us any advantage there? Okay, so yeah, so if you use some radial out bright background source, you don't like a quasar, radial out quasar or gamma ray burst, you don't really have to care about these strong foregrounds because now they are not much stronger than your this thing. So basically, what you need for your observation is just some high signal to noise spectrum from your from your quasar, and that should be in principle simpler to detect. But there is some problem or some challenge associated with that, which is how many radial sources do we have at high range? So we have many, do we have a few? That is the question, and I will discuss this how it looks now. Then another advantage is that when the spin temperature is equal to the CMB temperature, you can see 21 for a second. Can't do that with that's more or less how it's defined the node signal. So if this is equal for the global 21 centimeter signal, you will have no emission, no absorption, just no signal. This is not an issue in for a signal. However, if the intergalactic medium is hotter than say around 100 Kelvin, you see in there in the table, the absorption is reduced a lot. Technically, this is not really a challenge. This might be actually useful. That okay, if we don't detect signal, maybe you can learn something about the temperature of the IGM. If you want to really detect it, then well, maybe it might be hard. And we were talking about that it can grow small scale structure, which I think, to my understanding at least, is that this might be hard for 21 line observable. And given that this is my 21st slide, it's a good place to stop given the topic. So yeah, so the things that I want you to take away from this lecture is that what the 21 centimeter porous is, that it's a series of absorption features, a spectrum of distant sources, radial out quasars or gamma ray bursts, and this has some advantages which we just discussed. Might be simpler to detect, and because you don't care about these strong foregrounds. The strongest absorbers arise from cold, neutral, and diffuse intergalactic medium, so slightly overdense, and it depends a lot on the thermal and ionization state of the intergalactic medium. So yeah, so that's it. Sure, if you have any more questions, but given that soon Christmas season, I have some gifts for you. So please, so this was my first lecture ever. So if you can provide me some feedback, I'll be very happy. You can write this down. And another thing is homework. You can discuss it with me if you want. You can solve it. You don't have to for you. So yeah. And I don't know. You can just leave these feedback forms somewhere in the bag, or I'll collect them. They are anonymous. So yeah, thank you.